So I have real paper today. See how prepared I am? That one's right in front of me. So let's just go over some review. Just right now, just review. Go ahead and convert. Yeah, you good on that, right? That's just headache, right? We'll be on your quiz. No, it will be. Yeah. Yeah. So I guess I was going to do a review sheet for you on Monday, but I'll give you kind of heads up in case you want to get a head start on studying over the weekend. Is we did all that history stuff about back in the years. I'll probably ask you maybe 10 questions, 10 multiple choice questions on that stuff, history stuff that we did that very first week. I'll definitely ask you at least 10 questions on like CPU, architecture, and stuff like that, right?
Is it all in the slides, or is it
Yeah, slide, almost every bit of it in the slides. Just grab the slides. Okay. And also, but if you take a look at chapter 1, the slides are directly from the book anyway. So if you just went through the book, you can have it. Yes, sir.
Will you be uploading the rest of the slides? I know it's only on a big form on there.
even on?
Really?
Yeah.
Yeah, I know. It's schizophrenic, right? Okay, so this number stuff is going to be on your test. All this number stuff, except for I won't ask you to add the ones complement, twos complement numbers. We'll do that. We'll do that after the test. I will ask you to multiply and divide by shifting. We'll do that today. We'll do a little bit on floating point, but I don't think I'm going to ask you that on the test. The test, this will be a really easy test. I like to get started really, I like to really get that really success. So this will be a fairly easy test. It also is only 15% of your grade, so if you really do on average, I got you well, then at least we'll tell you. So, yes, sir.
Will there be any questions, like additional questions where we'll have to recognize overflow, or will they just be straight up?
Yes, I might ask you, like, and I haven't really developed the test yet, but I might like put a check box beside all of it and say if there's no overflow, check it. And so they'll all have a place where you can check for overflow. So yes. Okay. So let's go ahead and multiply now. So you do this the same way you do with base 10 multiplication. And I'm sure you guys are all fairly good at math. So it's 1. You take this and multiply it out. Same thing here. See, I'm getting all out of line. And now, the nice thing. It's either a 0 or a 1. So when you multiply by 0, it's always 0. When you multiply by 1, it's always the same thing, right? So it's pretty easy. Add this up. 0, 0, 0. I know I'm really not lining this up very well. Oh, what do I do now? Just like when we added before, 1 plus 1 is 2, so we have a carry, right? Okay. Okay, so add those guys up. 2 carry. Here's a carry, right?
Yeah.
Okay. So I have a double carry. I had a double carry, so I had a second one. Okay, so let's do this, let's take an extra step. I'd like for you to try these now, so. Multiply, don't cheat, multiply 25, and I'll keep these numbers small for you. And first, convert to binary. And then do the multiply. Let me get that worked out. So you have to do this in your test. Pardon me?
Did you put in 0 data involvement? Because they almost match up, but there's.
And. Sure.
Yes, sir. I did, I thought it was 137. I didn't know when to start at. See,
Yeah. So why are we working with 6 digits?
yeah.
And the reason we are is because these numbers can be so long, these problems can be so long. I just left off the leading zeros.
You'll tell us on the test.
Yeah, for sure. In fact, you can just on the test. I won't require you to use leading zeros. And the main reason is because then the problem is going to be really long.
So we'll do like 5 or the 32 bit.
Yeah. But you could work with more. I'm just doing this because I need to get tired.
Yes, so we would add 2 zeros onto these, both of them.
Yeah, to make this.
Yeah, I'm just checking.
Yeah. So and those would be like the leading zeros. now we get to a really interesting thing. And we're going to do assembly language in this class after the test. After the test, we're going to start assembly language. And so you kind of learn this on a really low level when we do that. Why would I say low level? What's the difference between assembly language, say, and maybe Java? Maybe Java.
Isn't Java compiled into the assembly?
Yeah, at the very end of it is. Yeah. But Java, we call it a high-level language just because there are so many layers from the actual source code down to the machine. But assembly is right directly, it's right directly at the metal level. So assembly, there's nothing that's between the actual language and the software. So the software and the hardware are just, they're together. So the higher level language, the slower it is usually, the less control over the hardware you have, and higher level languages usually make things easier to program. Okay, so let's say we have something, we have a binary number, and I'm going to keep this short. What's that value? 3, is that 11?
1, 2, and 8, 7.
Is that 11? Now we have this operation in assembly language, which means it's built into the processor's architecture. Okay, so if you can do it in assembly language, the processor has to stand up. There's something called a bit shift. Be careful how you say that. And you can shift right, or you can shift left. You can shift 1 bit, 2 bits, however many bits you want. Okay? So here's my 11. I'm going to write it down here. So if I shift it to the right by 1, all the bits move. And then I'll pad this with a 0. This moves there, that moves there, that moves there. And unfortunately, this guy is lost. 0, 1, 0, 1. And the lost fella is out here. He's contract. He's lost. So there is something we're going to talk about called an arithmetic shift right and an arithmetic shift left. And what those do is that those have a carry, so you don't actually lose the data. And also, the processor, when you do shift off and you lose data, then it shifts off, it sets one of the flags in the processor. So you can actually use it even though it shifts. But what value do I get here? What's my new value? It's 5, right? Okay. Do you see a relationship between 11 and 5? Maybe it's not obvious. Okay. So these are integers. What would happen if I was to divide 11 by 2? Now you're going to say 5.5, but there's no such thing if we're doing integer math. Okay. So we got a round off here when we do integer math. So what would the answer of 11 divided by 2 be? 5, correct? And any odd number, you're going to lose that. You're going to lose precision. So let's say you have 35 divided by 2, you get 17, right? Or let's say you had 43 divided by 4. What would you get there? Integer math. You get 10, right? So you have to realize anytime we do integer math, you're going to lose data. And is that good or bad? Depends. You know, that reminds me. They asked Bob Dole, boxers or briefs. You know what he said? Depends. Okay, so it really does depend. Let's say you're doing graphics on the screen, and each pixel is one discrete place. You can't have a pixel and a half, or a fourth of a pixel. cancel, right? You have just, you always have an even number, a discrete number on the screen, right? But what if you're working with your bank account? You don't want to lose any data there, do you? So in certain cases, you don't want to lose data. In other cases, you don't really mind so much. Okay. Well, why don't you just always have these floating point numbers? Never lose them. Why that would be true? Why not just always have 5 and a half, 4, 3/4, whatever? Well, because of speed. So these integer operations actually are a lot faster. Normally, an integer multiplier divide on a processor is 2 machine cycles. Okay. If they have a calculator, 2 machine cycles would be how many nanoseconds? It'd be ridiculous, right? Take what, 3.6 gigs? 2 divided by 3.6 gigs, I mean, it would be a ridiculous short period of time. But the divide with floating point numbers is 200 machine cycles. Which 200 machine cycles still is pretty small in the big scheme of things. But let's say you're in this big loop and you're doing a whole bunch of calculations. Eventually, it really adds up. So there are most things in computers are done with integer math. That's just the way it is. So back to bit shifting. So we talked about bit shifting right. And left. And we said it could be 1 to n bits. Okay.
So on 10, you ask us to shift.
Yeah, I'll give you a number and I'll say bit shift is to right 4, bit shift is to left 7, or it won't be 7 this week. And what I'm going to do is try to give you small numbers, just so there's no sense in giving you big numbers. I just want to make sure you get the idea. So,
And this is PowerPoint as well.
pardon me?
Is this PowerPoint as well?
No. I think though. I do have PowerPoint slides on this, and so I'll find them. I don't think I can get them uploaded for Monday, so, but that'll probably be the only thing I've missed until Monday. So I should have podcasted this today. Okay, so I might even consider not putting it on the desk.
I'll post a video online.
Pardon me?
I can post a video online.
You have a video online for this?
Yeah, I'm recording the class. No.
Oh, he's our hero. Awesome. Thank you very much. So, are you going to put that on video? I mean, on YouTube or something?
I'm gonna put the link on the web course.
Okay. So there you go.
My internet doesn't work.
If that doesn't work, oh, yeah, we're going to be really cautious. Okay. I appreciate that. We all really appreciate that. Okay. So let's go back to our bit shifting. 1 0 1 0. We already had some similar. Let's bit shift this two places to the right. First of all, what's its value? Its value is 10, right? And let's bit shift it 2 places to the right. So that's going to be, and we're going to have these with zeros. Okay, so. What the heck did I do wrong here? Right. What now? Is that right? Yep. All right, now. Let's try another one. 0 1 1 0. And let's bit shift to 3. And that value is 2 plus 4 is 6, right? So when I bit shift that 3, I'm going to get a grand total of 0, right? So, so we get 0. I described this the totally wrong way. That's what's bothering me. It's not divided by 2 and divided by 3. It's divided by 2 to that power. So however many you bit shift. And the reason for that is because this is the power of 2. So let me write out the clear rule. When you bit shift, n, it is the same as dividing by 2 to the n. Okay, that's what I should have said. That's not right. So let's go ahead and verify that. Let's have 4 examples. 1 1 0 0 1 0 1 1 0 1 1 0 and 1 1 1 1.
Would the dividing be only to the right and decline to the left?
You are so smart. You're way ahead of me.
I was just asking.
No, that's the way it works.
Okay.
Yeah.
Okay.
And that was a very good question, because that is the way it works. Okay. The question was, so going to the right, do you divide? Yes. What happens when you go to the left? Anybody have a guess for that? Well, okay, we'll get to that in just a minute. Okay, so what do we have? 4, 12, 8, 9, 10, 11, 6, 15. Okay, so let's bit shift this. 1, 2, 3. Well, we know what's going to happen if you did that bit shift that before. It's going to completely roll off. Let's do that too. Can you work with that? Pardon me?
If you were to bit shift that last one, 4, the answer would be 1.
No, it'd be 0. They all roll off. Now,
Okay.
here's how you could mitigate that with that arithmetic shift right that I was telling you about. We're not going to, I don't even think we do that when we do assembly language, but there's something called an arithmetic shift right. You can mitigate with that. So there are actually three these bit operations. Just the simple bit shift where you lose data. There's arithmetic shift right, arithmetic shift left, and then there's something called roll right, roll left. And roll right means you never lose any data, it just rolls around. Always just rolls around this way. So you can use that a lot for like graphics, like when you're shifting like a character or something, or a letter or something like that. Okay, so let's work these out. So go ahead and do that for me, please. First do binary values. So then tell me what those decimal values are. Crap. It's just, just trying not to get that value, but oh well, that's so much for good intentions. 6, 18. Really straightforward. And this is easier than converting decimal binaries. Okay. Next, let's do some multiplication. So in here, what we're going to have to do is as we shift left, we're going to have to probably pad a little. So the number of digits make it bigger. So 1 0 1 0. If we bit shift this to the left, I say one place. Now, I say that if you have an 8-bit number and you bit shift to the left, they drop off. If you have a 16-bit number and you shift to the left, they drop off, 32 and so forth. They will drop off. It depends on your size. Your processor has different size registers. It has 8-bit registers, 16-bit registers, and 32-bit registers. It depends on how big your register is. So, and we'll learn this next week. If your register is 8 bits, you shift over, and something drops off, it's then you've lost it. Same thing. So, but for right now, we're not going to get past 8 bits. Okay, so here we go. We shift this left, and as we shift it to the left, we go 1, 0, 1, 1. We just pad the right with a single 0. Okay. So this value was 3 plus 8, 11. We like that number 11. And what is this? This is 2, 6, and 16. This is 22. That was magic. Now, here's the question I'm asking. Are we going to get integer multiplication errors, roundoff errors? Why not? Because even if you start with an odd number, it will become an even number, right? Even times, no matter what you start with, you'll always have an even number, correct? So you won't have any kind of integer roundoff errors. Unless, of course, the bit rolls off the end and you lose it. Then you're totally toast. Okay, 1, 1, 0, 1. Let's bit shift this left. Say 3. This will give me a pretty big number. So our first, our 11 again, right? Okay. So let's shift it 3. So we'll pad this with 3 zeros. 1, 1, 0, 1. We didn't exceed whoops. Okay. So it's 64 plus 16 plus 8. Bless you. 8. Is that 88?
Yeah.
So we multiplied it by 8, right? And that's the same as 2 to the third, correct?
Yeah.
Okay, so that's how that works. This is pretty easy, and then, oh, come on, maybe Google it. Do you guys understand?
Yeah.
Yeah. You guys are IT. Okay. So the only thing is on Monday, we'll go into floating point numbers and make one million tests. I just make that executive decision. Right now, I want to talk about mutexes, and I want to talk a little bit about parallel computing, what I sort of missed. And I don't have slides for this, so what I'm going to do is in real time make slides so I can upload them. What?
Type it up, it should come up.
No, if you can run PowerPoint on this thing, because these things are so locked down.
I think they might have some on Google. Like the, yeah.
Google Docs?
If you open up some of your PowerPoints and you just start doing.
Oh, that's right. That's the way to do it.
That too.
Yes. It'll let you run PowerPoint if you're just opening your own slides. So, I really don't mind using Google Docs. Do you guys use Google Docs very much? I use it for everything. Probably the NSA knows my most intimate private details. Okay, so this is. Okay. The first thing we have to talk about is what is the process. Okay, the process is an EXE that the OS spins up. So a process is Internet Explorer, is PowerPoint, is fill in the blank. Can you have multiple processes for the same program? The answer is yes, right? I mean, typically by the end of a working session, I have 70,000 copies of Chrome on my computer alone. That's an exaggeration, but So, but a process is an instance of an application. So you can have multiple processes of multiple instances of Chrome or IE or Word or whatever, okay? So that's a process. Multiple instances of indices all as separate processes. Okay? But now what comes of that is threads. Threads are separate execution sections which processes spin up. Okay, so let's have some real life examples of what a thread is. So, yes, sir. Oh, I see.
Feel like multiple windows of Safari. Maybe one process of multiple threads.
Correct. So let's say you had multiple windows, multiple Safari tabs open or whatever, or let's say you had an application that one thread might maintain the pull-down menus, another thread might maintain, say, the music that is playing, and another thread might maintain whatever. So one process can spin up multiple threads. Now, there's something really interesting is that threads normally, especially the threads that are using a lot of the CPU, develop what's called thread affinity. So threads, what I meant was core threads develop core affinity. What that means is threads generally will stay on the same core. But the operating system manages all threads, and at a certain point, if one core is sort of getting more than its fair share of use, it'll shift maybe some threads, one or several threads over to another core. So what it does is it tries to balance threads, and that's why I say if there's a thread with fairly high CPU usage, it'll normally stay on a single core. Now, of course, this computer is not going to show you anything. So let's give it to Old Faithful here. Let's go to Task Mangler. Oh, this is Windows 8. Performance. So it gives you the different cores. You guys have seen this, I'm sure, but basically, the OS is going to try really, I don't see the different cores. What? I wish. Wait, I'm open this up so I can show my different cores.
I think it's under view.
If you go to open resource center at the bottom, you can also
It's right there on the right side.
Where is it?
Go down.
Yeah.
Third on the right, on the third word down is this course. Okay. And
If you reach for Flutter, it'll have some graphics on it.
on that on the bottom.
Very good.
Windows 8 is awesome.
Who said that? Okay, so now am I seeing, I'm still not seeing separate
CPU tab up
What
top. The CPU tab
Yeah,
up
which is
top.
overview CPU memory. Right there. Just scroll down.
It's not-
Another second.
We scroll down.
All right.
Over it to more.
To the right one.
Go to the right.
The far right.
Here.
Yeah.
Oh, I see. Okay, so it's showing all my separate CPUs. And you'll notice that if I open like IE, I wonder if I can do this with it. So get an idea of what's going on there. You'll notice that this will have some sort of process. It did have some sort of it probably spun up more than 2 threads, but you can see that this bottom core didn't get touched. So whatever threads that ID spun up, they develop their own core thread.
Probably did if you scroll down.
Pardon me?
63 probably did if you scroll down.
Ruining my whole story.
I mean, to be fair, only 2 of those are 2 full cores. The other 2 cores are just integer only.
I think these are 2 cores that are using what's that called, hyperthreading or something?
No, they're using the MD equivalent on Bulldozer, which is basically 2 full cores with integer and floating point, and then the other 2 cores per se are like partial cores that are primarily integer.
It's actually really an expensive laptop. Now I do have 6 full cores at home, and it's interesting to watch those. And I'm still using Windows 7, which is even better. Okay, how many of you really like Windows 8? Some people do. What do you like on it?
Honestly, I mean, other than, once you find your way around it, most even the resource management stuff is really nice. If you're sitting in the task manager, for example, just looking at different processes, how that's represented now versus how it was before, the heat map is a huge improvement, especially like managing Windows Server 2012 or 2012 R2 versus 2008 or anything
No, I
before.
use Windows 2002 and I like that.
But I said 2012 for the server.
Yeah, I use that. That's, my server is running 2012. And I do like that. I still haven't dropped it, some people just get left in the dust. So, all right, so those are threads and processes, okay? Now, software needs a way to manage this. And I'm not talking about task manager. So let's say I'm writing a program, and let's say I have a user interface object, like a label or something, right? And let's say one thread sets the value of this label, and another thread sets the value of this label. Good or bad? Yeah, it's synchronized, it's really good, but it's not. So how do you synchronize? So what you're saying is you need some sort of synchronization. What you're saying? Okay. So what he's saying is that software engineers, software developers have to figure out a way to make sure that that is not a problem, that they have some sort of a way to sort of referee what happens between processes, right? And especially gets bad when one process is writing to the screen and another process is trying to write to the screen. Or especially bad when they're both trying to go to disk and write to the same disk file. I mean, imagine that database. How many users does the server, MySQL or Oracle support simultaneously? I mean, SQL Server really has no hard limit. There is a realistic limit. There's no hard limit. So imagine you have this database in SQL Server, and you have all these web servers hitting the same database. How are you going to manage? And they're all really going to the same resources, which in effect are disk files. I know you can say, there's a lot of in-memory stuff going on. So how do you manage all this? Well, there are some things in programming. All programming languages have things that manage all this. The first thing is that they have the ability to spin up threads to make the user experience better. So if I have SQL Server and he has to wait until your query is done and you got all your data before his query runs and he gets his data, after a while your web server is really crying, right? Okay, so the first thing is all software developers have tools that give them the ability to spin up multiple threads. Okay. So we'll call this thread.one. Anything about object-oriented programming. All right. The next thing you have are called critical sections. Okay. And those are sections, those are pieces of code that the the software engineer blocks off is only one process could be in that block of code, executing that at one time. Okay? And so I have a server application that I wrote, and it takes like multiple connections at the same time, and it's gotta be thread safe. But there are a couple of things within that. There's a very narrow window of stuff that only one thread can execute. So what I do is I created a critical section so that everybody, the other threads that are coming in to execute that piece of code have to wait until he's at it, and then he has to wait until everything. And it's not a bottleneck because it's just a really short piece of code. And as long as you're not like doing a whole bunch of stuff that takes a long time, you're okay. So there's the idea of critical sections. The next idea is called semaphores. It's like Gilligan's Island. So what do you think a semaphore is? A semaphore is just a signal that I'm doing something. Say, for instance, I'm updating the database, say, your order record. Well, I might want to set a flag just so that someone else knows that I'm in the middle of updating your database record, okay? Giving you a raise or something, right? So there's a semaphore, and that's just indicating that it's a flag. And then the last thing is called a mutex. So a mutex is something where it's okay for multiple people to be in here, but once I get to say 10 or 15 or 20 in here, then something bad is going to happen. Okay? So a mutex is sort of a cross between a critical section where you can't be in here and it being wide open. It says, okay, in this section of code, there is a certain number of people, a certain number of threads who can get through there and be in there at the same time. So mutexes have counters, and they know how many threads are inside of them. And when one person leaves, when one thread leaves, they decrement their count, so they remember that. So that's how you do parallel computing. Okay, that's all there is to it. It's actually really complicated when you get into it, but those are the main. And by the way, I'm going to start giving you homework after the test. I'm sorry, really sorry I haven't given you very many assignments. You don't be too sorry, do you? After the test, I've got to ramp up the homework a bit, so I'll try and make it easy. Questions? Comments?
So we just need to know if it was getting test.
Yeah, actually, that's the end of chapter 1. Parallel computing is the end of chapter 1. Okay. That was reinforcement. All right, see you guys. I'll have a study sheet on Monday.
Chapter 1, right?
Yeah.